Boom, Julian, welcome. Now we are entering chapter 4. Oh, yes. In the former chapter, we had an amazing experience with God's law, and we said so many things about God's law. If you have not really understood that chapter, listen to that audio again. And I believe you will have a very perfect understanding because the way I made that explanation, trust me, it was very, very easy to understand. All right, so now we are going to be looking at electric potential. Electric potential is actually divided into two broad topics. You have electric potential energy, which is measured in joules because it's energy. And then you have electric potential itself, which is measured in volt because it is actually in the form of current, right? But it's actually joules per coulomb because it is the ratio of quantity of energy to the quantity of charge. All right, so let's start with the first one there, electric potential energy. First, I wanted to have an overview between the difference between electric potential energy and electric potential. Electric potential energy is simply the energy required. I wanted to say simply, the energy required to move a charge within an electric field created by another charge. That is electric potential energy. But when you want to talk about electric potential, this is simply the energy required to actually bring a charge positioned at infinity within the electric field created by another charge. That is electric potential. So, if I want to move a charged particle within the electric field created by another charge, I will make use of electric potential energy. But if I want to bring a charged particle from infinity, mind you, infinity does not mean a distance unending. It simply means a position outside the circumferential influence of the electric field of a charge. Once it is an inch outside that circumference of the electric field, it is at infinity. So bringing it within the electric field, you need electric potential. As for the energy, you move the particle within the field. And because the charge we are talking about is positive, and the electric field, or let me say, and the test charge you are moving within the field is also positive, so you're going to be experiencing some kind of repulsion. So you need quite some energy to be able to move a charge within that field because of the opposing force, the repelling force, both of them will be experiencing in the process. Good. So now I have to go deep into this chapter. First, electric potential energy is represented by U, and it is the work done in moving a charge within an electric field, right? And that work done is equal to force times distance. And the force we are talking about is from electric field intensity, which is equal to EQ. And if you substitute that in that formula, U becomes EQD. D can be taken as R because it is a distance, right? It's simply the distance between the charge you're moving and the charge that is stagnant. So your first formula will become U to be equals to EQR. Now, if you want to now change the value of U, of E, to KQR squared, still from electric field intensity, then you will end up having your new U to be KQ, capital Q now, small q, divided by R. Now, the capital Q is the organ that generates the electric field. The small q is the charge you are moving within the electric field. So, if electric field intensity is KQ over R squared, and you substitute that in EQR, R will cancel one of the R's, you'll be left with K, so capital Q, small q over R. And that is still the energy required, electrical potential energy required to move a charge within that field. Now, an exam question can come into play, and you are told that you want to move a charge positioned at this place in the presence of the electric field on the same line. Maybe you have two positions, point A and point B. Point A is the position where the test charge is right now. Point B is the position where you want the test charge to go to, on the same line with the charge generating the field. So what will be the work done in moving it from point A, where the test charge is, to point B? That work done is simply UA minus UB. UA is the potential energy at point A minus the potential energy at point B. If at the end of the day you have a negative answer, it means that more work is done by an external force. In other words, work is done by an external force to move that particle to that position. If, however, you have a positive answer, it means that the work is done by the system, right? Very, very important for you to remember. Good. Now, I still have one charge generating his own electric field. Now, I want to bring a test charge from infinity, that is outside the electric field, into a particular position within the electric field. I'm talking about one charge now, not two charges. One charge, Q. And I'm bringing Q naught into a particular position within the electric field generated. What will be the formula for the electric potential energy required to bring that charge into the field? And that will simply be E equals, or simply say U is equal to KQ over KBQ small q over R. Now, because you have two distances, first, the distance where the object is, the charge is now, and then the one that is coming from infinity. I think I'm a little bit having a big confusion here, but I think I'm going to address that very well. First, you have to understand that electrical potential energy is KQ naught in bracket 1 over R. Because you are bringing one from infinity, it becomes 1 over R minus 1 over R infinity. So 1 over R infinity is 0 because 1 over infinity is 0. So on that note, the electric potential energy that you will need to bring a test charge small q into the electric field generated by a big Q is simply KQ small q over R, which means we didn't do anything new. Yes, you did not do anything new. Why? Because 1 all over R infinity is 0. So the same formula applies. Just take the magnitude of that test charge and multiply by Q all over R, and that gets you done. However, if you have two charges now, two charges positioned at their various position, and they have their electric field, and you want to bring a test charge from infinity into a position there, it will simply be the work done by those two charges. So the work done by those two charges with respect to the foreign test charge you are bringing will determine the potential energy required. So what is the work done by these two charges? That will determine the potential energy required. So the potential energy of these two charges is equal to the work done in bringing a foreign charge within them. And for you to calculate the potential energy between them, it is simply KQ, because you are bringing a small q into play, call it Q3. So that becomes KQ1, Q3, all over distance between 1 and 3, plus KQ2, Q3, all over the distance between 2, Q2, and 3. So you have to be very careful with that. And that will give you the work done in bringing a foreign charge from infinity to a particular position within the electric field generated by those two charges. Very, very sacrosanct. Now, what if I have three static charges? They are not moving. They are just statics. They are not moving at all. How do I calculate the total potential energy generated by these three group of charges? Simple. Simply calculate the energy generated by each twos of the three charges. What do I mean by each twos? Q1, Q3, Q2, Q3, and then Q1, Q2. Just get the energy and then make sure that the distance are respectively based on their distances. So the total kinetic potential energy becomes K in bracket Q1, Q3 all over R13. That means the distance between R1 and R3 plus Q1, Q2 all over the distance between R1 and R2 plus Q2, Q3 all over the distance between R2 and R3. So that will give you the total potential energy. And that marks the end of electric potential energy. But I don't want to quickly jump into conclusion because I didn't mention superposition principle. Superposition principle. What is superposition principle? When you have a test charge Q surrounded by many other charges and you're asked, what is the potential energy required to move that test charge that is surrounded by other charges? The work done in moving that test charge surrounded by other charges that creates the electric field is simply the algebraic sum of the potential energy each one has in contact with that test charge. How do we mean? U becomes KQ. The Q naught now is the guy that all of them are focusing on. Then open your bracket, Q1 all over the distance between the guy, the focus, and the charge, R1, plus Q2 all over R2, Q3 all over R3, like that till ad infinitum. Very, very important. You have to take note of this because it is sacrosanct. All right, so that takes us to electric potential. What is electric potential? As I said before, from the beginning of this step, electric potential is simply the energy required to bring a test charge from infinity to a particular position in an electric field. Electric potential. However, electric potential is also defined as the potential energy per unit charge in an electric field. Per unit charge. Electric potential is the potential energy per unit charge in an electric field. And that simply means that V, it is represented by V measured in volt, and which is joules per coulomb. So that means V is equal to U over Q. U is the electric potential energy, which is force times distance, which you have already known to be equal to what? KQ all over R. That's KQQ not all over R, stuff like that. So by the time you start with your variance, first, you remember that U is equal to FD, which is equal to, and F is equal to EQ times R. So your first formula for potential, electric potential becomes V equals to ER. Why is it V equals to ER? Simply because you have been able, no, you're getting it wrong. The first formula is going to be V is equal to EQR. That's the first formula. Then the second formula, you now want to change the E, which is the electric field now, into, you now want to change the electric field into, sorry there, I think I made a mistake there. Let's start back again. Electric potential is simply the potential energy at any point in time per unit charge, isn't it? Good, that is U over Q, right? And U, as we already know, is force times distance, which is EQR. Now, for me to get the formula of potential, electric potential V, it becomes EQR all over Q. So when Q cancels each other, you have ER. So V is equal to ER or ED, as the case may be. R is simply separation distance, not radius. Now, having settled that, I can also substitute E to be equals to KQ over R squared from electric intensity. So if I substitute that inside, I'm going to get V to be equals to KQ over R. You get it? And take note, these values of V can be positive or negative depending on the charge of the particle. Never you ever ignore the charge of any particle when calculating potential, electric potential, because those charges are sacrosanct. It can be negative, it can be positive, depending on the charge. If the charge is positive, you have a positive potential energy or positive electric potential. If it is negative, you have a negative potential. Very, very important. Take note and never forget that. And then also, work done can also be in terms of kinetic energy. That is when the particle is in motion. And when that happens, your V becomes equal to your work done, which is kinetic energy, becomes a half mv squared. And work done, as we already know, is force times distance. And force is EQ times distance. So you can either calculate Q or calculate V. If you're asked to calculate a potential, you can make V the subject of the formula and you just get your job well done. So remember that is sacrosanct. And then it's also important for you to know how to calculate the electric potential at any particular position in an electric field. Very important. The electric potential at any position in an electric field, I wish you could picture this diagram in your mind, because this diagram is obviously what you need to have a perfect understanding. But I'll try my best to explain it in a way you will understand. I have a straight line. In that straight line, the ending of that straight line is point A. Then next to that straight line, is a charge Q1. Next is a point B. Next to point B is a charge Q2. Next to the charge Q2 is point C. And next to point C is a charge Q3. Now the distance between Q1 and point A is R1. The distance between point B and Q1 is R2. The distance between point charge 2 and A, so the distance between point B and Q2 is RB. The distance between charge 2 and point C is R4. The distance between charge C and charge Q3 is R5. I hope you understand. Good. So at this point, if you're asked to calculate the potential, the electric potential at A, it is simply the charge all over the distance to that point A times K. In other words, potential, electric potential is KQ over R. So the electric potential at point A will simply be K in bracket, the charge, which is Q1, all over the distance between that charge and point A, which is R1. Plus, because there are multiple charges now, about 3 charges, plus charge 2, all over the distance between charge 2 and point A, plus charge 3, all over the distance between charge 3 and point A. And that will give me the electric potential at point A as a result of those 3 charges. Now, what if I'm looking for the electric potential at point B as a result of those 3 charges? I will first of all have to look for the closest charge, which is charge 1. Charge 1, that is Q1, all over the distance between Q1 and point B, which is R2. Then plus Q2, all over the distance between Q2 and point B, plus Q3, all over the distance between Q3 and point B. Same thing with point C, and you'll get that. This is also called superposition principle. Yeah, in the presence of multiple charges Q1, Q2, Q3, the net electric potential at a given point is obtained by the superposition of the electric potential of the individual charges in the electric field. That is what we have just demonstrated. Then the last thing we are going to study about this chapter is equipotential surfaces. An equipotential surface is simply a surface where the potential difference at any 2 points equals 0. That is to say, there is no work done in moving a test charge from one position to another within that surface. It is referred to as equipotential surface. And usually, equipotential surfaces, their potential difference, or simply put, their V is always equal to 0. Why will it be equal to 0? Because they are of the same distance. And by the time you find a difference, you will get 0. You will see a question like that. So just remember, equipotential surfaces are surfaces in which the potential difference at any 2 points within the same is equal to 0. And usually, the charges will contribute to the zeroness of the 0. Because one charge is going to be positive, one charge is going to be negative, and they are equidistant to that particular position. So there you refer to it as equipotential. And then take note, if you have an earth is a perfect example of an equipotential surface, and all conducting materials as well. They are perfect examples of equipotential surfaces. So if you have a circle, divide it into 2 diagonals, about 1, 2, 3 set of diagonals, you have charge with the diagonal that is the diameter that is horizontal to the x-axis. You have Q1, Q2, and Q3. And then you have 3 points at the surface hemisphere as point A, point B, point C. Point A is an equipotential point between Q1 and Q2. Point B is equipotential to Q2 and Q3. And point C is point B is at equipotential between Q1 and Q3, because that is where the angle will make a very, very equal position. Then C is the equipotential point between Q2 and Q3 respectively. And that marks the end of this amazing chapter, and it's important you take note. But before we declare this chapter an end, let me just chip in this. When a particle is suspended in air between 2 charged plates, then the electric force on the particle is equal to the gravitational force on that particle. That is to say, if you are able to suspend an oil or something between two charge plates, just know that the force of gravity is equal to the electric force. And the electric force we're talking about is EQ, and the gravitational force we're talking about is mg. So from there, you can medal out your work and solve the problem given to you right away. Thanks for listening. This is Jolivan, and we are good to go for the next chapter, which is capacitors. Boom.